Hello, my name is Ian Sisson.
And I'm Patrick Bonner, and we simulated the fluid flow over a roughness element.
Now, understanding how fluid flows around a roughness element has many practical applications. It can provide aerodynamic improvement, turbulence mitigation, and higher energy efficiency. And examples of surface perturbation prevention include flush-mounted rivets on aircraft. We can see in Figure 1, they are not using flush-mounted rivets, which provides surface roughness, which can create turbulence. So by using flush-mounted rivets, it creates a smoother surface on a wing of an aircraft. Winglets on aircraft wingtips also prevent vortices, which can lead to turbulence. And having smooth transitions between perpendicular surfaces are ways that we use to prevent turbulence and surface perturbations. Industries that are benefited by this knowledge are the aviation and aerospace industries, the automotive industry, and the construction industry. Now, data collected for the simulation was done previously in another research project. They physically conducted the experiment using temperature-sensitive paint, also known as TSP, and it is the industry's choice for temperature visualization of fluid flow. TSP creates color gradients based on relative surface temperatures. It uses LEDs and a camera to collect this data. A free stream velocity, also called U infinity, is a defined fluid velocity upstream from the roughness element. And water is chosen for this experiment due to its predictable interactions. Beneath the temperature-sensitive paint layer, there was a heated plate, which allows the temperature-sensitive paint to create these temperature gradients. And their experiment was 117 centimeters by 30 centimeters by 7 centimeters.
Before we get into the bulk of what we did this year, it's important to discuss some important vocabulary words that relate to fluid dynamics in our project. So the first one of these is a horseshoe vortex, which is a vortex that is formed when a fluid flows around an object in a shape of a horseshoe, as demonstrated in Figure 3. And a boundary layer, which is a thin layer of fluid near the surface where the velocity changes from 0 to the free stream velocity or the velocity of the water. And a roughness element, which is a small object within the flow of fluid that creates the changes in the fluid flow, which is in Figure 4. And we use ANSYS CFD for our project, and CFD, or Computational Fluid Dynamics, is a program that simulates complicated fluid flow. It uses Navier-Stokes and continuity equations to solve fluid systems, and these equations are shown in Figures 5 and 6. And it is used for verification and validation in the real world. It is also important to consider the boundary layer simulation and the effects that it has on the roughness element downstream of the wake. The Blasius boundary layer simulation was naturally formed over a non-slip condition surface with a free stream velocity of 0.04 meters per second. The Blasius boundary layer solution equations are shown in Figure 7, and this is how we calculated the graph on the right, which is Figure 8. And we compared our simulated Blasius solution to the actual equations that correspond to the Blasius solution. When solving a computational fluid dynamic problem, there are typically 4 steps that you would follow. The first one is setting up the geometry for your simulation. And now, because our simulation was large and would cause problems if we did it in one simulation, we broke it up into 2 separate simulations. The first one was an inlet simulation, which had dimensions of 42 centimeters by 30 centimeters by 7 centimeters. And this was a channel that the water developed the correct Blasius solution that matched the one done in the experiments. And then their simulation contained the roughness element, and this was 75 centimeters by 30 centimeters by 7 centimeters, and it was a channel. And it also contained the roughness element, which was had a diameter of 3 centimeters and a height of 3 centimeters. The second step for a CFD problem is setting up the mesh, and this is what allows the program to solve your problems, solve your Navier-Stokes and continuity equations for you, and we used a standard linear mesh. And the next step for CFD problem is to set up your initial conditions. And our initial conditions were it had an initial velocity of 0.04 meters per second and a Reynolds number of 380. On the figure 9 shows the geometry of the simulation with the reference element, and figure 10 shows the same simulation but with the mesh. And this is an image of the mesh zoomed in so that you can see the linear nature of it. And the next step for CFD is the results.
So in the results section, in figure 12, we measure the Q criterion vorticity. We can see that pulling around the roughness element, and it creates these bulges on either side that resemble, I guess, aircraft wings. That converges back into the center into two tails, essentially, where they dissipate about halfway down the simulation. And this just gives a visual representation of what the vortice looks like three-dimensionally in the simulation. And the results on the left are the results that were completed in Germany on the previous research project. We can see the horseshoe vortex or tails have a low coefficient of friction. We can also see that in the wall shear stress in figure 14, where the same effect occurs. We can also see the recirculation zone in both figures, with it being about 1 diameter behind downstream the roughness element in both images.
And the figure on the left shows the velocity contour in the x direction. The maximum velocity in the x direction occurs toward the middle of each vortex, as you can see in the red. And the minimum velocity for the x direction is shown in the recirculation zone just past the roughness element. And the figure on the right shows the free stream velocity contour toward the bottom of the plate, and this just shows the direction of the flow is moving from left to right. Yeah. And then in summary, the interaction of a boundary layer with reference element is studied using a simulated approach. The simulation results show formation of a horseshoe vortex, which wraps around the front of the reference element and extends into the wake of region past the element. The wall shear stress signature of the horseshoe vortex compares well with the structures observed in the experiments using temperature-sensitive paint over a heated surface performed by the German Aerospace Center. And the next steps include a simulation of a heated plate and the variations of the Reynolds number in the flow.
And here are our sources, and that is our research project.
Yes, thank you.